Logarithmic differentiation, part 2. A quick reminder that you should know your properties of logarithms, and that these are the derivatives of logarithmic functions that we'll be using a lot. In particular, we're going to be using a lot of this chain rule with the natural log function. So we have y is equal to the natural log of tangent x times x cubed plus 2 all over the square root of 3x cubed plus 4. Now, if we were trying to take the derivative as is without simplifying anything first, we'd have to use chain rule, where this natural log of x is on the outside, and on the inside we have this tangent x and everything there. We'd have to use quotient rule on that quotient. To get the derivative of the numerator, we'd have to use product rule, and to get the derivative of the denominator, we'd have to use chain rule. So that'd be chain, then quotient, then product, then chain again, and that is a huge mess. And if we can avoid all of those many rules in one problem, it's probably a good idea to do so. This whole mess is inside that ln, so we can use our logarithmic properties to simplify it a bit. So we have y is equal to the natural log of tangent x plus the natural log of x cubed plus 2 minus 1/2 the natural log of 3x cubed plus 4. So I just used log properties to simplify that. And you want to be able to go from here to here just as quickly as I did. And if you're not quite sure how I got from here to here, that means you probably need to practice properties of logarithms a bit more before you really get into work with logarithmic differentiation. Because you want this prerequisite skill of expanding these expressions to not take up any space in your brain at all. You want it to be nice and automatic so that you can focus your heavy thinking skills on the actual differentiation process. In the meantime, this came from the product in the numerator that we split up. And then if you're dividing by something on the inside of a log, we can split it up with subtraction. And this 1/2 comes from the square root of that entire 3x cubed plus 4, which is the same as to the 1/2 power. Now that we've split this up, we can use some differentiation. So we have dy dx is equal to, and we use chain rule very frequently with logarithmic differentiation. So this is the natural log of this tangent x. So we have a function and a function, and we use chain rule. The derivative of the outside function will be 1 over whatever's inside of it. So that'll be 1 over tangent x. The derivative of tangent x is secant squared x. So this is the derivative of our first piece. And then we have the derivative of the natural log of x cubed plus 2. The derivative of natural log is 1 over whatever is inside of it. So that'll be 1 over x cubed plus 2. Times, using chain rule, the derivative of what's inside of it. The derivative of x cubed plus 2 is 3x squared. So that's the derivative of the second piece. And then we have minus 1/2 times, because this is a constant times a function, as opposed to just a constant all by itself, so it follows us along. We have the natural log of this 3x cubed plus 4. So the derivative will be 1 over whatever's inside of it. So 1 over 3x cubed plus 4 times the derivative of what's inside of it by chain rule. So that'll be 9x squared. And then we just want to do a little bit of simplification. So dy dx will be equal to secant squared x over tangent x, which you could simplify a little differently if you wanted. But right now we're just trying to make it so that our quotients are nice and lined up instead of multiplying like they are. So this next one will be 3x squared over x cubed plus 2 minus 9x squared over 2 times 3x cubed plus 4. And that is our derivative. And using those log properties and then just a bunch of chain rule is typically going to be a lot easier than using a combination of chain rule, quotient rule, product rule, and more chain rule. So a lot of people prefer this part of logarithmic differentiation because it makes it so the derivatives are easier to take. Next up, we have y is equal to the natural log of e to the x squared secant cubed x times tangent 3x. So let's use our log rules to simplify this a bit. So we have y is equal to the natural log of e to the x squared, which normally I'll simplify a bit more in one step, but I want to break it down for you, plus the natural log of secant x, which is being cubed, plus the natural log of tangent 3x. And we can simplify this further. So this is y is equal to x cubed times the natural log of e. Well, the natural log of e is just 1. Plus 3 times the natural log of secant x plus the natural log of tangent 3x. And now this is looking much nicer. Rather than having to use chain rule and multiple product rules, we just have to worry about a little bit of chain rule and these derivatives of natural log functions. So taking the derivative, we get that dy dx is equal to the derivative of x squared is 2x, plus this 3 follows us along since it's not a lonely 3, it's a 3 times a function. So we have 3 times the derivative of natural log is 1 over what's inside of it, so 1 over secant x. And then using chain rule, we have to take the derivative of what's inside of it. The derivative of secant x is secant x tangent x. Plus, now we have another chain rule with a log function, so that'll be 1 over tangent 3x times the derivative of tangent 3x, which will be secant squared 3x, times the derivative of 3x, which is 3, which I ran out of room for. And then we just want to simplify a tiny bit. So as I look at this, I'm both dividing and multiplying by secant x, so those will divide out. And now we have that dy dx is equal to 2x plus 3 tangent x plus 3 secant squared 3x all over tangent 3x. And that is the derivative. So frequently, when functions have this logarithmic function inside, particularly natural logs, it becomes easier to take their derivative if we can use properties to simplify first.